This short video will help you make the most of the formula book in your A-level pure maths examination. We'll look at the formulas, we'll look at some related formulas, and we'll look at exam questions that illustrate their use. Let's start with the formulas for arithmetic series. You're told that the sum of n terms of an arithmetic series is a half n a plus l, the first plus the last term in the series, or a half n 2a plus n minus 1d. So this is for the generic series a plus d, a plus 2d, and so on, the nth term of which is a plus n minus 1d. You'll need to know how to prove this formula. First, we write the sum in one direction, starting with the first term, ending with the nth term. Then we write the series in reverse order, starting with the nth term, going back to the first term. What we note is that the pairs of terms in these two sequences will always add up to 2a plus n minus 1d, or the first term plus the last term. So if we add the two equations, we get 2s on the left-hand side, and it equals n sets of 2a plus n minus 1d. And therefore, this sum to n terms will be n over 2, 2a plus n minus 1d, or n over 2, the first plus the last. The general tip for solving arithmetic series problems is always try to identify and calculate the first term and the common difference. Moving on to geometric series, again we may be asked to prove these two formulas. The way it works is this. We write the sum to n terms equal to ar plus ar squared, and so on, up to ar to the n minus 1, the nth term. A is the first term, r is the common ratio. We then multiply both sides of this equation by the common ratio r, and we get rsn equals ar plus ar squared all the way up to ar to the power of n. If we subtract the second equation from the first, these pairs of terms will all cancel, and it will leave us with Sn minus r times Sn equal to a minus ar to the n. We can simply rearrange this to give Sn equals a times 1 minus r to the n divided by 1 minus r. If the absolute value of the common ratio r is less than 1, then the term r to the n will tend to 0 as n tends to infinity, and therefore the sum to infinity will tend to a over 1 minus r. Let's look at an example question. Here we're asked to find the value of sigma between r equals 4 and infinity of 20 times a half to the power of r. So this is the sum of a geometric series. The first term a is 20 times a half to the power of 4, which equals 1.25, and the common ratio is a half. We substitute it into the formula for the sum to infinity, and we have s infinity equals 1.25 over 1 minus a half, which equals 2.5. Next is the binomial series. This first binomial expansion is for the natural numbers. The second expression here for the binomial expansion is for when the power is a real number. What's happened here? The n minus r terms of n factorial have been cancelled with the n minus r factorial in the denominator. Let's see an example. We're asked to use binomial expansions to show that the square root of 1 plus 4x over 1 minus x is approximately 1 plus 5 over 2x minus 5/8 x squared. We have the formula from the formula booklet at the bottom of the page. The first job is to rearrange this expression into a form whereby we can use the expansion below. We write this expression as 1 plus 4x to the power of plus a half times 1 minus x to the power of minus a half. And we're going to apply the binomial expansion for each of these terms separately. Looking at the first term, 1 plus 4x to the half. The power is a half, so n is a half. The x that we're using is 4x. So we have 1 plus a half times 4x plus a half times a half minus 1 over 2, 4x all squared plus terms in x cubed and above. This will be valid when the absolute value of 4x is less than 1. That is, when the absolute value of x is less than a quarter. For the second part here, 1 minus x to the minus a half, we have 1 plus minus a half times minus x. And then we have minus a half times minus a half minus 1 over 2 times minus x all squared, plus terms in x cubed and above. This will be valid when the absolute value of x is less than 1, which it will be if the absolute value of x is less than a quarter. Next, we simplify each of these expansions, being very careful with the fractions and calculations of each of the coefficients. So here we get 1 plus 2x minus 2x squared, and for the second expansion we get 1 plus a half x plus 3/8 squared. We multiply these together, simplifying the coefficients. This is approximately equal to 1 plus 5 over 2x minus 5 over 8x squared as required. Let's move on to trig identities. There's a whole list of identities provided which allow you to expand and combine trig functions. The double angle formulae aren't provided, although these are easily derived by setting a equal to b. So for example, sine of a plus a equals sine a cos a plus cos a sine a. So sine 2a equals 2 sine a cos a. I'd like to look at an interesting application of sine a plus b, and that's when we have to solve something like 12 sine a plus 5 cos a equals 7. Here what we'd like is for the 12 to represent a cosine of b and the 5 to represent a sine of b, so that we can combine the two terms using this formula. So we draw a triangle with height 5, base 12. We calculate the hypotenuse, which in this case is 13. Sine theta will be 5 over 13. Cos theta will be 12 over 13. Tan theta will be 5 over 12. So we can calculate theta, 10 to the minus 1 5/12, which equals 22.62 degrees. Now we return to our original equation and we rewrite it as 13 times 12/13 of sine a plus 5/13 of cos a, and this equals 7. Now we switch the 12/13 for cos theta and the 5/13 for sine theta, and now we have a pattern that matches our trig identity. So we have that sine a plus theta equals 7 divided by 13. So a plus 22.62 degrees, the value we calculated for theta, is sine to the minus 1 7/13, which can equal 32.58 degrees, 147.42 degrees, and so on, depending on the range that's given for a. Therefore, a can be 9.96 degrees or 124.80 degrees, and so on. We're also given the small angle approximations for the trig functions. So sine theta is approximately theta, cos theta approximately 1 minus theta squared over 2, and tan theta approximately theta. Notice here theta must be measured in radians. It's not true if theta is measured in degrees. Sometimes you get very simple questions based on this. For example, given that theta is small and measured in radians, use the small angle approximations to find an approximate value of 1 minus cos 4 theta over 2 theta times sine 3 theta. Here we simply substitute 4 theta into the small angle approximation for cos theta and 3 theta into the small angle approximation for sine theta to give us this expression, which is easily simplified to 4/3. Differentiation from first principles. You may be asked to derive the derivatives of sin x or cos x from first principles. Let's look at how this is done. For fx equal to sin x, f dashed x will be the limit as h tends to 0 of sin x plus h, that's f of x plus h, minus sin x, that's f of x, all divided by h. We can use the difference of two signs from the trigonometric identities to rewrite this as 2 cos x plus h over 2 sin h over 2. We rewrite this with h over 2 as the denominator. We apply the small angle approximations for sine. Sine theta is approximately equal to theta. So for small h, sin h over 2 is approximately equal to h over 2. So that these two terms will cancel, leaving cos x plus h over 2. And as h tends to 0, cos of x plus h over 2 will tend to cos of x, which is what we needed to show. You're provided with a list of standard derivatives. The formula at the bottom shows you the derivative of a quotient, f of x divided by g of x. I'm more used to seeing this in the form of d by dx of u over v equals v du dx minus u dv dx over v squared. In fact, it's this method that is used to differentiate tan, sec, cot and cosec using the derivatives for sine and cosine. You're not given the formula for the derivative of a product. You need to know this. It's an important formula. So d by dx of uv is u dv dx plus v du dx. Almost a little bit of poetry. It also provides the basis for integration by parts, which we'll look at later in the video. Integration. Again, we're provided a list of standard integrals. Let's look at the case of y equals ln of x. If y equals ln of x, then x equals e to the y. If I differentiate x equals e to the y with respect to y, I get dx by dy equals e to the y, which itself equals x. So dy by dx will be 1 over x. This shows us why the integral of 1 over x is ln mod x plus c. We put a mod x in there because you can only have logs of positive values. This model is what's used to derive the standard integrals. The last bit of integration is the recipe for integration by parts. Let's look at an example. Use integration to find the exact value of the integral between pi by 2 and 0 of x sine 2x dx. You have to choose a suitable u and v to enable you to use the integration by parts formula. Here we're going to choose u equal to x and the dv by dx equal to sine 2x. This will give us the integral of u dv dx as the integral we're trying to evaluate. Lay this out clearly. Calculate the derivative of u. So x differentiates to 1. Calculate the integral of dv by dx to find that v equals minus a half cos 2x. Now we have these four expressions. They can be substituted into the recipe for integration by parts. So this will give us the integral of x sine 2x dx equals uv, so x times minus a half cos 2x, minus the integral of v, and v is minus a half cos 2x, so this becomes plus the integral of 1/2 2x, times du dx, which is 1 dx. The first part has already been integrated, so now we need to integrate the second part of the right-hand side, which will give us a quarter sine 2x. We don't need a constant of integration because it's a definite integral, so when we put our limits in, we get the limits between pi by 2 and 0. Sine of pi by 2 and sine of 0 will both be 0. Cos of pi will be minus 1. So when we substitute pi by 2 into minus a half x cos 2x, we get pi by 4. And when we substitute the 0 into x cos 2x, we're going to get 0 because of the x being 0. Next, let's take a look at numerical methods. First, the trapezium rule. The trapezium rule approximates a definite integral by splitting the curve into a number of equally widthed vertical trapeziums. The width of each trapezium is h, b minus a over n, and n is the number of strips. Let's look at an example. We're given the curve y equals 5 to the x plus log to the base 2 of x plus 1 between x equals 0 and 2. We're first asked to complete the table of values. So here we substitute x equal to 1, and 5 to the 1 plus 2 log 2 of 1 plus 1 will be 5 plus 1, as log to the base 2 of 2 is 1, which is 6. Here's the curve. You won't need to draw it. We simply substitute these values into the expression above. So it's a half, 0.5 for the width, the first y ordinate plus the last y ordinate, and twice the sum of the middle ordinates. This is a convenient way of summing the area of these trapezia. Doing this on the calculator gives us 17.56 to 2 decimal places. Note that because this is a convex curve, the trapezium rule gives an overestimate, as the size of the trapezia exceed the area under the curve. Finally, we're going to look at the Newton-Raphson iteration for solving the equation fx equals 0. This gives an iterative formula where xn plus 1 equals xn minus f of xn over f dashed of xn, the derivative of fx at xn. Let's look again at an example. Here's our equation. 2x cubed plus x squared minus 1 equals 0. So in this instance, our fx is 2x cubed plus x squared minus 1. We'll have to work out the derivative. That's straightforward. It's 6x squared plus 2x. And we'll need to work out what x minus fx over f dashed x is. We get this expression, which can be simplified to give us 4x cubed plus x squared plus 1 all over 6x squared plus 2x. This gives us the iterative formula for calculating the root of fx equals 0. The question continues. Using the formula given in part A with x1 equal to 1, find the values of x2 and x3. So what we need to do is to substitute x equals 1 into this formula to work out x2, and then substitute x2 into this formula to work out x3. I'm going to show you how to do this calculation using the answer button on the ClassWiz calculator. First of all, we type 1 equals into the calculator so that this will put the value 1 into the answer store of the calculator. Next, I'm going to type in the iterative formula using the ans key instead of the xn. I type the equals and it substitutes the current value in the answer store, namely 1, into this expression, and it gives us a result of 3/4. This will be the value for x2. This will also be the value now in the answer store. I type equals again and I get 2/3. So this is the value when 3/4 is substituted into this recipe, and so is the value of x3. Each time I press the equals key, I will get the next value generated by the iterative formula. If I keep pressing it until the value given here doesn't change, I'll see that the root of fx equals 0 has been approximated to be 0.65729811061. So I get a very accurate approximation to the root. So we found x2 and x3. We weren't asked to calculate a detailed approximation to the root. We are, however, asked to explain why, for this question, Newton-Raphson method cannot be used with x1 equal to 0. If we tried to substitute x1 equal to 0 into this formula here, I'd have a 0 denominator, and therefore I wouldn't get a value for x2. In other cases, You may find that your starting point creates a sequence of values which will not converge to a root. So this can be another reason why the Newton-Raphson method will fail. Okay, that's all. I hope you found it useful and that you'll take a look at the other videos in this series. Goodbye.